Hi dear students, this is the 8th part of 4th module of the subject EST 100 Engineering Mechanics. In the last presentation we were discussing about the kinetics, and we have seen the lift motion in that case, and we have done some problems also. Now in the second case we will move on to the topic, that is motion of the connected bodies. So how connected bodies are moving and how we can calculate the acceleration. Same principle, D'Alembert's principle we will be utilizing here also to calculate the acceleration and velocity and all. Okay, we will explain that concept with a simple problem. So the concept is simple, nothing is there. We will be considering the dynamic equilibrium F minus ma equals 0, or simply we will be making that body in equilibrium. Actually the body is moving, connected body is moving, but we are assuming that the body is in equilibrium by providing a inertia force m minus ma, or inertia force ma is applied opposite direction to that of the motion, so that the body is kept in equilibrium. That is what is known as the dynamic equilibrium. That is the basic concept. So coming to the problem, a body of mass 4.5 kilogram is placed on a smooth table at a distance of 2 meters from the edge. So this is that body, 4.5 kilogram mass body. Actually it is mass, not weight, remember. So from this is the table, from the edge of the table the body is kept at a distance of 2 meter. So this distance is 2 meter. Next is, the body is connected by a light string passing over a smooth pulley. You can see a string passing over a smooth pulley, and the other end we are having another body, and the other end of the string is connected with a body of mass 2.5 kilogram. The mass of this second body is 2.5 kilogram. Here the mass of the first body is 4.5 kilogram. Find acceleration of the system. First we want to find out the acceleration of the system, and second one we want to find the time that elapses before the body reaches the edge of the table. So at what about the time required this body to move till the end of this table, that is what is, or the time required by this body to move 2 meter. That is the simple explanation of this one. So time that elapses before the body reaches the edge of the table. So what the time required by the body to reach from here to edge of the table, or the time required by the body to cover a distance of 2 meter. That is the meaning. Now I can't say it as actually a free body diagram, but for the simplicity I am explaining this as a free body diagram. If I am this is the connected body, entire body. So I am drawing the free body diagram of the first one. So you can see this 4.5 kilogram mass. I am drawing the free body diagram. There is a table will be there. Here you can see frictional coefficient and all is not given. That means there is no need to consider the friction. Otherwise we have to consider the friction also. Here the weight of the body will be acting always downward, since it is a horizontal table. So weight is 4.5 into 9.8 in mass into g, that is the weight. A string is connected to this body. That means on the string always tension will be there. Tension will be always away from the body. So tension T is acting in this direction, and we know that the body is moving in this direction only. It is clearly given in the question. Body is moving towards the edge of the table. Edge is towards this direction. So body is moving in this direction. That means this body is moving downward and this body is moving towards the right. That is the direction of the motion. This direction of motion is very important, since we have to apply inertia force opposite direction to the motion of the body, then only it will be in equilibrium. So direction of the motion of the body is very important. So this body is moving towards the right, so inertia force I have to apply towards the left. That means ma I have to be applied from right to left, then only the body will be in equilibrium. So dynamic equilibrium is tension will be acting in this direction, weight will be acting downward, and inertia force, that is m into a, 4.5 into acceleration, where a is the acceleration of the body. So that acceleration will be acting in this force into acceleration, m into acceleration is acting opposite to the direction of this body. So with all these forces this body is in dynamic equilibrium now. I think the concept is clear. You first mark all the forces acting on it one, and think about in which direction the body will be moving. Opposite to that direction you just apply a force ma. That's all. So this is the equilibrium diagram or free body diagram. So now along the x direction, if you are taking sigma fx equal to 0, then what happens is x direction T is acting in this direction, 4.5 a is acting in the opposite direction. So t is equal to 4.5 into a. So that is our equation 1, t is equal to 4.5a. From that you got an equation relation between t and a. Now sigma second free body diagram, there is nothing to do with the sigma Fy in the first case. So I am considering the free body diagram of the second one. So this is the free body diagram of second body. The weight will be acting downward. 2.5 to 9.81 is the weight of that body, and of course the tension will be there in the string at the other side. That is here tension is acting in this direction, here tension will be acting in the opposite direction. Both end tension will have the always the tension will be away from the body. That is, here the tension is in this direction, here tension upward direction. So the tension is acting upward, and as we know the body is moving downward. So inertia force we have to apply in the opposite direction to the motion. So I am applying inertia force m into a, 2.5 into a, in the upward direction. So net force, what about the net force? Net force here it is along the direction of the motion, you have to take it as positive. So 2.5 9.81 minus t, that is the net force, equal to 2.5 into a, that is our equation. Or net force minus 2.5 into a is equal to 0, that is 2.5 9.81 minus t minus 2.5 into a equal to 0, that is what is written here. Or you can simply write as you can take it as sigma Fy equal to 0, sigma Fx equal to 0, no problem, once the inertia force is also marked. So after marking inertia force, you can directly write as sigma Fx equal to 0, Fy equal to 0. Whichever you seems convenient, you can use that concept. Both will give the same result. So I am following this one, sigma Fy equal to 0. In the y direction, this I am taking as positive t plus 2.5a, since both are acting in the upward direction, but this is opposite direction. So minus 2.5 into 9.81 equal to 0. So you will be thinking that here actually 2.5 into 9.81 is acting in the downward direction and t in the upward direction. So this term has to be taken as positive. Okay, that also is right. In that case, you have to write 2.5 into 9.8 minus t equal to 2.5 into a. That is very important. Here I have already marked the direction of 2.5 into a as the direction opposite to that of the body. That's why I am writing sigma Fx equal to Fy equal to 0. Once it is correctly marked, then you can take it as sigma Fx equal to 0, Fy equal to 0, no problem. So t minus 2.5 9.8 is equal to 2.5 minus 2.5 9.81 equal to 0. From that you will get another relation between t and a. Since it is connected through a pulley, both will have the same acceleration. First body, whatever the acceleration of the first body, the same acceleration will be there for the second body. So a is same and t also same, since it is the same string. Therefore t and a are same. So from 1 and 2 we have 4.5 into a equal to 2.5 9.81 minus 2.5a. So from that, solving two equation, two unknown, you can directly solve it and you will get a is equal to 3.5 meter per second square. So that was our first part. What about the time acceleration required, acceleration of the body? That is our first part. So we got the answer. And then next one is the time required by the first body to move till the end of the table. Here we know that the distance that body has to move is 2 meters. So s is 2 meter. Initially the body was in rest, so u is equal to 0. Now time taken we want to find out. Acceleration we already got it as 3.5. So in substituting s is equal to ut plus half a t square, you will get this term as u is 0, so this term is 0. So half a t square, from that t square equal to 1.14 and t is equal to 1.06 second. That is our answer. Now next problem is an engine of weight 500 kilonewton. See, the weight of the engine is 500 kilonewton. Pull a train weighing 1500 kilonewton. The rest of the bogie will have a weight of 1500 kilonewton. So weight of the engine is 500 kilonewton, bogie weight is 1500. A lot of bogies will be there. So altogether it is weight is 1500. Plus engine it is 500. If engine weight is also ordered, total weight will be 2000 kilonewton. Engine separately 500 and bogie separately 1500. Up an incline of 1 in 100. That term is very important. So engine is pulling the bogies up an incline. Train is moving upward. Up an incline of 1 in 100. 1 in 100 actually what means is, if 100 meter horizontal distance is there, then the upward direction 1 meter will be there. If 100 meter horizontal, 1 meter upward. If 200 meter horizontal, 2 meter will be upward direction. So you can draw a triangle with 100 meter horizontal, 1 meter vertical. Then the From that you can find out the value of theta. So theta, there will be an angle, so one horizontal line is 100 meter distance and 1 meter upward direction. You can complete that triangle. So the theta is the angle connecting horizontal direction and the hypotenuse. So tan theta will be equal to 1 by 100. That is the meaning of 1 in 100. You will be familiar in questions and all, this term will be coming. 1 in 100 means tan theta equal to 1 by 100. That is the meaning. That is the opposite by adjacent, that is tan theta. Tan theta equal to 1 by 100. If the theta value is very small, usually we will be assuming sin theta equal to tan theta. So if theta is very small, in that cases only we can assume that category, that this one, that is sin theta equal to tan theta. Both will have the almost same value. So anyway, inclination is given as 1 in 100, that means tan theta equal to 1 by 100. The train starts from rest initial, so u is equal to 0 and moves with a constant acceleration against a resistance of 5 Newton per kilonewton. So each kilonewton will be having a resistance of 5 Newton. So how will you find out the total resistance? That is frictional resistance, here it is talking about. So how will you find out the total resistance? If 500 kilonewton is there, means 5 into 500, that much Newton, sorry, 500 into 5 will be the total resistance. So if 1500 kilonewton is there, means 1500 into 5 will be the, that much Newton will be the total resistance. So resistance will be acting always opposite to the motion direction, that also you have to keep in mind. It attains a maximum speed of 36 km per hour in 1 km distance, within a 1 km distance. So h is equal to 1 km and final velocity is 36 km per hour. That we have to convert into meter per second. Here it is there. Final velocity, initial velocity is equal to 0, final velocity v is equal to 36 km per hour. 36 into 1000, that will be converted into meter. To convert hour into second, 60 into 60, so you will get us 10 meter per second square. Determine the tension in the coupling between the train and the engine and the traction force developed by these are the two quantities that we want to find out. First one is tension in the coupling between the train and engine. You can see one coupling will be there to connect the engine to the bogies. So what about the tension in that coupling? That is what first we want to find out. Then the next one is traction force developed by the engine. How much power is required by the engine to pull this one? That is what is tractive force. Okay. So initial velocity u is equal to 0, final velocity is 10 meter per second square, s is equal to 1 kilometer or 1000 meter. Now substituting, we know that v square minus u square equal to 2as. So v square, u is 0, so v square equal to 2as. From that you will get us a equal to 0.05 meter per second square. So acceleration of this train is 0.05 meter per second square, and it is given that it is constant acceleration, so anywhere we can take this acceleration. Anyway, we got the acceleration a is equal to 0.05 meter per second square. Now this is the case, this is our engine and this is the bogies, and the engine is moving upward, pulling this entire bogies. So the weight of this entire bogie is 1500 and engine is 500 kilonewton, so 1500 kilonewton. So you know that the weight of this bogie will, total bogie's weight will be acting downward, that is 1500 kilonewton will be acting downward. But this is a slope, actually it's an inclined plane. So if you draw a normal along this direction, then in between weight and this normal we have an angle theta. So that theta is actually given, we can find out from that equation, tan theta equal to 1 by 100. So from that either you can calculate the value of theta, or we are having some other options, I will explain it. Anyway, if you draw a vertical along this direction or to this inclined plane, then that vertical will make an angle of theta with this 1500 or weight. Okay. Anyway, body is moving, train is moving, bogies are moving upward. So inertia force we have to draw in the opposite direction. So inertia force is ma, m is the 1500. Sorry, it is in kilonewton. So 1500 divided by g into a, that is the, that we can see here. Okay, anyway, to find the tension in the coupling between the engine and train, dynamic equilibrium of the coaches only may be considered. So I am considering the equilibrium of this bogies only. Let T is the tension in the coupling. So tension in the coupling will be acting, as I told, always it is away from the body. So tension is acting in this direction. And there will be some resistive force against the motion. just like frictional force. So since the body is moving, train is moving upward, means the resistive force will be downward. That I am representing by the term P. So P will be acting downward. So to calculate that value, it is given here as tractive resistance equal to 5 Newton for each kilonewton. So here the total kilonewton is, total weight is 1500 kilonewton. So total tractive resistance is 5 into 1500. So that is equal to 7500 Newton. Why I am substituting this in kilonewton itself is 5 Newton tractive resistance is for 1 kilonewton. So 5 into how much weight in kilonewton is there, that has to be multiplied. So 5 into 1500. So this is to be in kilonewton itself. No need to convert to SI unit. Remember, since its unit here given, it is 5 Newton per kilonewton. For each kilonewton, 5 Newton tractive resistance will be there. That's it. So 5 into 1500. So totally 7500 Newton tractive resistance will be there. Resistive force will be there. Converting into kilonewton, it is 7.5 kilonewton down the plane. So component of weight is equal to 1500 to 1 by 100, that is 15 kilonewton down the plane. Why I am multiplying 1 by 100 is, if the theta value is very small, tan theta equal to usually sin theta. So the weight component along the motion direction is 1500 kilonewton along this direction, that is parallel to this surface. So here it is vertical, and this 1500 is making an angle theta. So if you are solving perpendicular to this surface, then it is cos theta component. If you are solving along the horizontal direction to this plane, then it is sin theta component. So 1500 sin theta will be the weight component, and it will be acting in this direction, that is opposite to the motion direction. So sin theta, as I told, if the theta value is very small, then tan theta will be equal to sin theta. So sin theta equal to tan theta equal to 1 by 100. So that's why I am directly substituting this 1 by 100. Another option is, you can directly calculate the value of theta. Theta equal to 1, tan theta equal to 1 by 100, you know. From that you can calculate the value of theta, and now calculate the value of, by substituting the value of theta, you can calculate the value of sin theta and substitute here. That is 1500 into sin theta. That also is okay. 1500 into sin theta, then you will get as 15 kilonewton down the plane. So remember, this weight component is acting, the horizontal weight component will be acting down the plane. Actually train is moving. So now we want to find the net force, and along with the net force we will be considering the inertia force also. Inertia force is nothing but W by G into A. Okay. So inertia force is equal to W by G into A. W is equal to 1500, actually it is in kilonewton, by 9.81 into 0.005. Acceleration is 0.005. This much kilonewton is the inertia force. Now since all the forces I am taking in kilonewton, that's why I have taken this also in kilonewton. So now if you write about the equation of equilibrium or dynamic equilibrium equation, if you are writing, then I am taking this direction as positive, T minus this P value is actually 7.5 kilonewton, T minus 7.5 minus this one, that is 1500 and 9.81 into acceleration. That term we got it as 7.645 kilonewton. So T minus 7.5 minus 7.645 kilonewton minus 15 kilonewton. That 15 kilonewton minus, so the net force are T minus 7.5. 7.5 is tractive resistance, that is P. So T minus P minus inertia force is, you got it as 7.645 kilonewton. That also is the 7.645 kilonewton minus the weight component of this one along the direction of that of the plane, or horizontal to the surface. So that we got it as 15 kilonewton somewhere here. This is that one. That is 1500 kilonewton into sin theta. That is 15 kilonewton. So substituting everything, only unknown quantity is T. You can get the value of T acting, or the tension in the that connecting body coupling is T equal to 30.145 kilonewton. That is the answer. Okay. Now one more part we have to find out is to find the tractive force developed by the engine. How much power actually engine has to provide in order to pull all these bogies. That is our second part. So I am considering the entire body together, that is bogies plus engine. I am taking it as together. And one more option is there, either you can take engine alone. If you are taking engine alone, then one tension will be there. in this direction. If this is engine, one tension value we have already got from the earlier calculation, that also we can, in that case also you can do. Otherwise you can take the entire body as one, that means total weight will be 2000 kilonewton, bogie plus engine weight is 2000 kilonewton. So I am taking here as the total body. You just try the other way also, just draw the free body diagram of the engine alone, and P is the force exerted by the engine to pull the bogie. So P is acting in this direction since the body is moving along this direction, so power is to be applied along the motion of the direction. Some tractive resistance will be there in the opposite direction, R I am taking it as R, and of course inertia force is equal to total the total weight by G into A, that is the inertia force. It should be marked opposite to the motion direction. So this is the free body diagram of the entire bogie plus engine. So I am writing the dynamic equilibrium equation. So before that I am calculating each term, then it will be very easy. Total tractive resistance, as we have told, for the each 1 kilonewton the resistive force is 5 newton. So 5 total here, total weight is 2000 kilonewton. So 5 into 2000, 10,000 newton will be the total tractive resistance. So R value is 10 kilonewton. 10,000 newton means 10 kilonewton down the planes in this direction. Inertia force is W by G into A. W is 20,000 kilonewton by G into acceleration is 0.05. So you got it as this much kilonewton. Now component of the weight down the plane. So component of this 20,000 along the plane. So that is 20,000 sin theta. As I told, sin theta is 1 by 100. Sin theta will be equal to tan theta, that is equal to 1 by 100. So 2000 into 1 by 100, 20 kilonewton will be the inertia force. Now dynamic equilibrium, if you write the dynamic equilibrium equation, then you will get as P is the force exerted or the power of the engine, that is in this direction. I am taking it as positive. So P minus 10, what about the 10? Tractive resistance R value, P minus 10 minus inertia force is 10.194. So minus 10.194 minus 20. 20 is the component of the weight in this direction. So minus 20 equal to 0. From that equation you will get the value of P equal to 40.194 kilonewton. So engine should exert this much power, then only we can pull the bogies. Okay, that is the problem. So as I have told earlier, instead of drawing the free body diagram of this one, we can individually draw the free body diagram of the engine. In that case what happens is, there will be engine will be there, instead of this 2000 kilonewton weight, 500 kilonewton weight will be acting downward, and instead of this R, the R value will be 500 into 5, that much newton, that you can convert into kilonewton. And along with this power P, here we will have a tension T in the opposite direction. That tension we got it as 30 point something, that is 30.145 kilonewton, that was the tension. And inertia force will be, instead of 2000 by G, here it will be 500 by G into A. A will be same, since it is total body is taken, total body will have the same acceleration. So both engine and bogies will have the same acceleration. So A is as 0.05 itself. So you just try with that case also, just try to do that problem, and I hope you will get the same answer. P is equal to 40.194. Just try it. Okay, I think the concept is clear for you. Thank you.